Okay, well, now let's make the transition from talking about the carrying capacity of various species, non-human species. Let's talk specifically about human population growth patterns and the implications they have on um, the global environment, which are basically really, really significant. So weird to think about it, but for most of the past thousands, millions of years, humans have, as long as we've been humans for most of that time, we didn't really have much impact on the ecosystem because not any more than any other organisms, because we lived in small groups scattered throughout the countryside. We basically acted as hunters and gatherers. So we gather grains and fruits, we'd hunt for protein, and the impact we had was very minimal. We didn't do much to alter our natural habitat. So we didn't have much of an impact on the ecology around us. But that all changed about 12,000 years ago, because about that time, humans began to discover in different parts of the world, like in the Indus River Valley, the Nile River Valley, the Tigris Euphrates River valleys. People started realizing, hey, wait a second. This I've been going out gathering food, but if I take the seeds of those things and plant it near my cave or my hut, it grows, and I don't have to look for it anymore. I can harvest it, and not only that, I can get more of it than I get looking for it in the wild. I don't have to hunt gazelles anymore. I can get other kind of livestock animals and train them to become domesticated, so they just live near me, and I can eat them when I want to. And what happened was two things. One thing is humans began to alter the landscape around them significantly and started to have a major impact on the environment around them, because they started clearing out land area to make farm areas. They started grazing livestock. Uh, and this had a big impact on the environment, where we didn't do that before. But the other big thing that happened was, well, another thing that happened was civilization. Okay, so we started building cities and walls, and we want to protect these crops and protect this livestock. So we have armies now. We have artisans, which is kind of cool. But we have this congregation of people. We have a congregation of people. We start to have sewage issues and disease issues. So the more impact on the environment. But the other thing that happened is that because we got really good at growing food, there was an explosion of resource availability. And anytime there's increased resource availability, if you think about a curve of carrying capacity, as there's more resources, the carrying capacity goes up. So there's going to be more organisms, in this case, more people. And when we look at human history, this is definitely the case. So, yeah, take this with a little bit of a grain of salt, because we don't really know for sure. But let's just consider this. So about 35,000 years ago, humans moved into places like the Americas and Australia. And so there was more land available, more resource. So lo and behold, the population increased. There's more people on the planet. But a really big thing happened around 10,000 years ago, about 10,000 BCE, about 12,000 years ago. People discovered agriculture, and suddenly, we had this ginormous increase in human population. So it probably went from about between 5 and 8 million up to about 70 million in about 5,000 years. That's a huge, just consequentially ginormous change in human population that occurred. But it didn't end there, did it? Because let's just look at this graph. It's a pretty good one. So if we go back in time, say to 10,000 BCE, human population is very small. We discover agriculture, human population kicks up. Now it goes along until we get to about 3,500 BC, about 5,000 years ago. People discovered plowing, they discovered irrigation, and suddenly there was a greater availability of food. So human population goes up again. Now, and it slowly climbs. The people develop more and more land becomes available. So it's not that there's new technology; there's just more land became converted to agricultural. So there's more humans. You would think that diseases would play a major role in decreasing a population, but it's pretty minor. So here's our bubonic plague, just a little dip. But then what happened is this: the Industrial Revolution. Once we learn how to turn coal to extract energy from coal to make steam engines, and then from oil to make internal combustion engines, we could have farm equipment, we could have refrigeration, we could have ability to transport things far away. And that just made a lot more resource available for human beings. That made a lot more human beings. And we're in the throes of that. Right now, we're essentially the human population is essentially growing at its biotic potential globally, not necessarily everywhere, like certainly not here in Korea, but it is globally. And that's just because there's so much resource availability. And here's the graph of it. And if that doesn't terrify you, I don't know what will. So basically, for the longest time, we're just barely growing, barely growing, barely growing. And all of a sudden, right? Man, we're skyrocketing upwards. Now, the reason this is worth paying attention to is there's a number of reasons why we should. But let's just start with this. We do not know what the carrying capacity of the Earth is in terms of human population. We don't know how many people it can feed. Now, there are a lot of smart people who've invested a lot of time and research into trying to figure that out. And the number they come up with is probably somewhere around 10 billion. They think that about 10 billion is about the number of people that can successfully stay on the planet without causing resource depletion. We don't know that. Now, so if we look at look at this curve. So here's human population growing, growing, growing. Here we are here. Now, well, there's three basic scenarios we might get. We could get the low scenario where population changes very quickly and starts to decline, like it's doing here in Korea, like it's doing in many developed countries. We'll talk about that in our next lesson. It could just continue to skyrocket at the same rate as it's going right now, which would be terrible for reasons we'll get to in a second. Or we could get something in between the two, which is probably most likely. But this in between one puts us over 10 billion people, which means we may end up overshooting and dying back, which basically means starvation and a lot of unpleasantness, which it'd be best to avoid by just looking at this curve, understanding it, and try to act on it before we get to that point. Now, back around 1800, there was this guy named Malthus, and he was basically an economist and a mathematician. He made this observation. He said, look, human population grows exponentially. Resources tend to grow linearly. The rate at which we make more land available, it tends to be at a pretty constant rate, but the rate at which we reproduce, because every time you have more people, then there's more people to reproduce. It naturally almost always leads to, if it's a growth, this exponential growth. And so what he said was going to happen is eventually you'll get to this crisis point. You'll get to where the human population surpasses its ability to feed itself, and you get what he called, well, what we called in his honor, a Malthusian Catastrophe. And he said, look, what's going to happen at that point? There's going to be famine. There's going to be people attacking each other to take their food. There's going to be disease. It's just going to be a lot of horrible things. This is what happens when human population overshoots its carrying capacity. He didn't have the concept of carrying capacity, but that's basically what Malthusian Catastrophe is. It's surpassing the carrying capacity of human beings, and it leads to things like starvation, famine and war and disease. Now, we came really close to this back in the mid part of the right after World War II, in the mid part of the 20th century, in certain places like India and Pakistan, China. There was basically the population was growing faster than the available resources, and people who understood this looked at these graphs and said, "This is going to be bad. We need to do something." And one of the people who really did something about it. Now, he didn't do it alone. He was part of like the Rockefeller Research Institute, but basically, man named Norman Borlaug. He was basically a plant biologist kind of guy, a forester, whatever. And he said, look, we can't make more land. That's not an option. That grows at a basically slow rate, like Malthus suggested. That's not really the option. What we could do, he suggested, is maybe we could like try to how to say this, breed crops that are more suited to producing more food per acre of land. And he just set about with breeding programs. And this is before he had genetic engineering. Although they did try irradiating plants to see if they get a higher rate of mutations, to see if they could get ones that would be more suitable. But essentially, he was able to come up with a number of very high producing crop species of wheat and rice and millet and things like that. So you could basically quadruple the amount of energy that you made, food energy that you could get out of a given piece of land. And it worked. I mean, they call it the Green Revolution. And it wasn't just these crop species. It was also using modern pesticides, modern herbicides, fertilizers. And these things were going to stay later in the year, lead to a lot of problems. But it did avert that Malthusian catastrophe in these countries. And as a result, he got the Nobel Prize. And it's pretty cool. They said, when they gave him the Nobel Prize, we're giving this to you because you have essentially saved 1 billion people from starving to death. That's a pretty cool thing to be told. I can't think of anyone else who has that kind of esteem. So let's just take a look at this. All right. So here's 1961, after the Green Revolution started. Here is what happened with the amount of land available to harvest. It didn't change. But here's what happened to the yield on that land. It went up as the human population went up. And so it was able to outpace population. And then what happened was, in those countries, the population began to stabilize. All as well for now. But things have changed in that between then and now. The human population has tripled since then. Okay, some countries have stabilized, but most of them have not. And so we see as the human population continues to climb, and once again we're confronting with a potential looming Malthusian catastrophe. This time in sub-Saharan Africa, and it could be really bad. And so we need basically a second green revolution. People are hoping maybe that genetic engineering can supply that. Again, that's something we'll study later. But for right now, I just want to point out that's one of the problems with population. Human population exceeds food. It leads to bad things for humans, but also these bad things for the planet. Okay, so let's just look at. I mean, you can make the argument that almost everything that is happening to our environment that is negative is a consequence of to humans on the planet. Okay, and so the increasing size of the human planet is really causing pressure, negative pressure, detrimental pressure on the environment. So let's just look. That means more people means more area has to be converted from natural area to agricultural land, right? And that means we have to cut down forests. That we lose habitat, we lose soil. All right, we have to irrigate that land, so we lose water. We had to put fertilizer on that, so we end up damaging the environment. With fertilizers and pesticides. We have to provide energy for those people, so we end up putting more carbon dioxide into the atmosphere. We had to provide them with goods that they need, and so that production generates toxic waste that get into our waterway. And through all this, we basically end up degrading the environment, so we end up losing habitat, biodiversity. It all goes back to population. If human population was smaller, these problems would be smaller and more manageable. So it is definitely in our interest to figure out what are the factors that drive population to increase and to try to find ways of mitigating that. That is the best thing we could do for our planet, apart from switching to non-carbon fuels. Okay, so if we're going to save the planet from ourselves, we have to figure out how to manage ourselves in terms of the rate at which we grow. And there's different ways of doing this. Now, and we'll talk about it in our next lesson. But for right now, let's just come to understand how we measure population growth. Okay, because we can't measure it, we can't study it. So basically, there's four things that are going to determine the size of a population: the rate at which babies are born, the rate at which people die, and for an individual country, the rate at which people move into a country, and the rate at which we call immigration with an I, and the rate at which people move out of a country, which we call immigration. I mean, immigration. You know what? It's like in Korea, I can't tell the difference between ba and pa, or piot and biot. Biok? I don't know. I can't tell them apart. So anyway, immigration with an I means people moving into a country. Immigration with an E means people moving out of a country. These four things collectively can determine what the population of a country is. Now, when we're talking about the planet, we can just drop the immigration and immigration unless there's aliens and people leaving the planet, like Elon Musk. I don't know. So we can just simplify and talk about birth rate and death rate. So let's just talk about birth rate. Birth rate is calculated by taking the total number of live births and babies that actually get born and divided by the population. Okay. And so here's just a sample population, here's an example. Okay, so let's just say that there's 1,350,000 babies born one year into a country that has 45 million people. Well, if I just take the number of babies born divided by the total number of people, I get 0.03. That's 3%. Sometimes we often express it as a percent, but when we try to work with it mathematically, a lot of times it's better to work this way, but not always, as we'll see. Now, the same thing is true for death rate. All right, so I basically, how many people died, take the total number of people who died, divide it by the total population, and you get the death rate as a percentage. You can do the same thing for immigration. How many people moved into the country divided by the total population? Immigration, how many people left the country divided by the total population of the country? So all of these rates are all calculated in the exact same way, and they make sense. I don't think much of us will have a hard time with that mathematic trick right there. All right, not too worried about that. And we've talked about this before. If birth rate is greater than death rate, assuming that we'll take immigration off the table for right now. If birth rate is greater than death rate, we'll get this exponential growth. And if we get a death rate that's greater than birth rate, we get basically an exponential shrinking of the population. But when the two equal each other, we get a stabilization of the population, like a carrying capacity. Okay, now this one seems a little bit weird, but it makes sense. Work with me here. We call it the natural rate of increase. And basically what this is like, let's take immigration and emigration out of the picture, and let's just focus on birth rate and death rate, okay? So basically, the natural rate at which a population increases is simply the birth rate minus the death rate, okay? If they're the same, then there is no rate of increase, right? If we have a 5% birth rate and a 5% death rate, 5 minus 5 is 0, I have 0% change in the size of the country. But let's look at the United States in 2017. The birth rate was 1.2%. the death rate was 0.9%. So if I say birth rate minus death rate, I see the country grew at 0.3%. That's not 30%, that's 0.3%. All right, that tells us how much bigger the country got. So we can use this value then to figure out how much population, how many more mouths are there going to be to feed, so to speak. Okay, so basically, if we say, all right, we have a population that's 18 million and it has a growth rate of 5%, which by the way is a pretty high growth rate, but it does happen. Okay, so let's say we have a 5% growth rate. We would just take the total starting population, right, 18 million. Then we're going to multiply it by the amount of growth that occurred, right? So basically, we're going to take the natural rate of increase as a percentage and multiply it by the population. So we had 18 million times, if it was a 5% growth rate or natural rate of increase, we say times 0.05. And when I add this to this, I find my final population is this. It went up by 900,000 individuals. Now, if the death rate exceeds the birth rate, what you end up with is a negative natural rate of increase. In other words, you have a natural rate of decrease, I guess. Okay, so it goes down by a negative percentage, and everything else is the same, except that I'm going to multiply by a negative value here. And so instead of having more people after my calculation, I have less people after my calculation. Now, let's no longer ignore immigration and immigration. Okay, so the two things that will add to the size of a population are the birth rate. More babies means more people, and immigration. More people moving in makes more population. And there's two things that make the population go down: people dying and people leaving. So death rate and immigration. So we could say that the total rate of growth for a country is going to be equal to the birth rate plus the immigration. That means these are the two things that bring people into a country, minus the death rate, because that takes people out of the population, minus immigration, because that's people leaving. So I take all these away, add these together, and that tells me what my growth rate is. So let's just look at an example of this, okay? So let's just say we have a population of 12 million people. The birth rate is 2.2%, death rate is 3.4%, okay? So we have a higher, like right now we have a negative natural rate of increase. The immigration rate is 4.3%. Lots of people want to move into this country. Economic opportunities, let's say. The immigration rate is low. 0.6 people want to leave. 0.6% of people want to leave. So what's the overall growth rate? I would just say, look, the two things that add to the country's population are birth rate and immigration with an I. 2.2 birth rate, 4.3 rate of immigration. And then I take away those two things that cause the population to go down. The death rate was 3.4%, and the rate of immigration was 0.6%. When I do my calculation, I get a total change of 2.5%. All right, so that is the rate, the actual rate of growth of this country, taking all the factors into account, all four factors. So if the question was instead, what would the population be a year later? If it started off at 12 million, what would it be after a year? So I basically use this calculation. I get 2.5% is my growth rate. That's the same thing as 0.025. So I'd say the starting value of the population plus, in parentheses, the starting value of the population times that percent change, which was positive. And then I end up getting a population, in this case, that was 12,300,000. Last thing, there's a concept called the rule of 70. And this is, you can use this for economics as well, for calculating how your investments are going to do. So basically, it's a pretty straightforward idea, not too hard to remember. It goes like this: that we often want to talk about when we want to compare populations, instead of talking about growth rate, we often talk about doubling time, because that kind of brings it to front, like this population is going to double in 5 years. Okay, so doubling time is often a metric we use to talk about different countries' population growth. And one way of finding it is using what's called the rule of 70. Okay, you can ask your math teacher why this works, but basically it goes like this: the doubling time in years for any population can be found by taking the number 70, always the number 70, and dividing it by the percent growth rate of that country. And that's taking into account, both immigration and immigration. Okay. Now, in order for this to work, you had to use that as a percentage. So you use 5%, not 0.05. Okay. So let's just take a look at this. So Pakistan has a growth rate of 2.1%. How long will it take for the population to double? So I say, well, the doubling time is equal to 70 divided by 2.1%. So it's going to double in 33.3 years. It's not so hard. You just had to remember the number 70. Doubling time equals 70 divided by that. What if I said it had a 70% growth rate? Well, that means 70 divided by 70 equals 1. It's going to double every year. Thank God that's not the case. what if I had a chart like this? And I said, well, what is the growth rate of this country? That can be a challenge, but here's the way you approach this. You try to figure out how long it took the country to double. So I'd say, well, here it was 30 in like 1960, and it was 60 in 1990, right? So basically what I say is it took about 40 years for the population to double. So therefore, I put doubling time equals 70 over this. So I'm just going to swap these two values with each other. So I'd say 40 years equals 70 over the percent growth rate. Now I swap those numbers, and what I get is the growth rate is 1.75%. So we're going to need to practice this a little bit. I know it's a lot to throw at you in one day, but this is kind of like the most of the nuts and bolts of how we calculate human population growth. And it's going to take a little bit of practice, and that's what we're going to do today. So thanks for watching this screencast and being ready to get started as soon as class gets going next time we meet. See you guys.